What is going on, YouTube? And welcome to the second video. This is going to be sorry, the camera's wobbly. This is going to be a continuation to our numerical analysis on matrix and vector norms. And this last time we were looking at this example with basically just the p-norm of a diagonal matrix, but we got cut off because my phone memory stuff. So anyway, and if you guys are watching this, thank you guys. So let's continue with this journey. Next, so the p-norm of a diagonal matrix, let D be our diagonal matrix, and then as in the second row of figure 3.1, which is basically the three properties of triangular inequality, scalar property, and if the norm can't be negative, and if it's zero, then the vector inside the norm is a zero vector, assuming vector norms. Cool. Yes. So then, yeah. So the image of the two-norm unit sphere under D is an m-dimensional ellipse, oh my gosh, whose semi-axis lengths are given by the numbers di. And what that is basically just this guy we were looking at last time. Cool. And so the unit vector amplified most by D are those that are mapped to the longest semi-axis of the ellipse. Yeah. But yeah, of length, taking the max of the absolute value of di. Therefore, we have d2, which is equivalent to the max as 1 is less than or equal to I, less than or equal to m, and with di, so value. And yeah, in the next video, we shall see that every matrix maps the two-norm unit sphere to an ellipse. Okay, yeah, sorry. And the property, oh wait, no, not the property. Yeah, and the name of this is a hyperellipse. Very sorry again, bear with me. And yeah, if m is greater than 2, though the axis may be oriented arbitrarily. Cool. we can say that this results for the 2 norm generalizes to any P if D is diagonal. Then the P norm of D is equivalent to the max DI. Now, bear with me for 1 second because I want to show you guys one connection, I believe. There was in regards of this, and yes, so well, yeah, in a sense this kind of relates to this property, which this is a matrix infinite norm, but it is equal to the max. So, gosh, yeah. So y'all can kind of see almost a little similarity going on right here. And that can be used for what I would think a proof, but just interesting. Anyways, back to it. We can just generally just say this line really kind of represents a good. The result of the 2 norm generalizes to any P if D is diagonal. Thus, the okay, cool. And that's the second example. Oh gosh, I forgot we're going backwards. Okay. Next up is example 3. So this one is the 1 norm of a matrix which states if A is any m by n matrix, then matrix norm 1 is equal to the quote maximum column sum of A. We explain and derive this results as follows. So we're going to write A in terms of its columns. Cool. And we're going to denote A as such. And this is used for an interesting property as well, this style, when you break it up in columns. I wish I could show you, but it's honestly a long process. in regards of explanation. So we're going to leave it for another time, but it is a good, we'll look into this. Just try to think of another way to do vector matrix or vector matrix or matrix multiplication. Just try to think of it like proofs almost, is what I would say. Anyway, let's get back into this. So this is A, where each A to the J is an M vector. Period. Consider the diamond shaped one norm unit ball in the complex of Cn. Illustrated in last video, which you can kind of say is these. Okay. Last video. And this is the set X. It's in complex of N, summation of N to the J equals 1. This should look pretty familiar. Any in the image of this set satisfies and this is a cool property. Cool. So anyway, we're gonna write a little proof. Actually, well, basic, which is a matrix times a vector norm 1. And we're going to break this up, denote it in its summation form. And we can say that this is, less than or equal to summation. And this is property 3.1, first property, or oh shoot, third property with the scalar. Oh, actually, well, yeah, actually, no, never mind. Sorry. Yeah. Max. One. And this kind of looks familiar to the infinity norm almost, right? Maybe, just saying. Anyway, therefore, the induced matrix one norm, we a little sip, my drink. Of course. some good stuff. All right. Therefore, the induced matrix 1 norm satisfies matrix 1 norm, and we can say it's less than or equal to the max, as we saw stated above. J approaches N. I don't know why my handwriting is straight dog right there, but that's okay. By choosing x can state it equal to e2 sub j, where j maximizes a to the j, a to the j, a sub j, norm 1, we attain this bound, and thus, yeah, I was scared I wasn't in the camera. The matrix norm is matrix A, 1 norm, boom. All right, and that is our mini proof, in a sense. Cool. So we got that from that, and yep, that's it for 3.3. Awesome, guys. And let's take one last look at the whole question if you need to. And now time for question 3.4. This one's going to be a little bit way easier. Oh gosh, the infinity norm of a matrix. So by much the same argument, it can be shown that the infinity norm of an n by n matrix is equal to the maximum row sum, denoted as such. Now this should look pretty familiar as we stated before. And just to mention, this is what the vector, I guess, infinity norm would look like. Same as the max property, and yeah, I guess you could look at it like that. So just something to think about. But yeah, anyway, yeah. And we can also say where AI star denotes the ith row of A. So just going down the rows. And yeah, I think that's where we're gonna end it for this video, because that's the end of this question. Let's look. And for those who made it this far, thank you, and we'll catch you on the next one.